This is my colleague, Muhammad Al-Ghairi.
Okay, شباب.
Our 10 project is titled by LSTM-Based System Identification of Quadcopter. At the beginning, we know that in model-based control, to design an effective controller, we have to get an accurate model. In other words, a good model improves controller performance and make the tuning easier. We know that there are two methods to extract the dynamical model of any system, using physics or first principles, or using system identification. System identification is a powerful tool as it makes us extract the dynamical model from data. And that's what we need when it comes to complex systems like quadcopters or humanoid or more complex robotic systems. Proper statement, we know that quadcopter is highly nonlinear with coupled and under-actuated configuration. To design an effective controller, we need an accurate model. We cannot achieve an accurate model using only the physics. So we go one step to throw a system identification. So we want a data-driven model that can learn a non-linear relationship between the input and the output of the quadcopter. So our goal is to use LSTM, long short-term memory neural networks, to identify the dynamic of the quadcopter, to improve state prediction and to be used for control design. Regarding the previous works, what we found that most of the literatures use nonlinear RX models, nonlinear RX model like structure, where the model have two main parts. The two main parts is the regressors, and the first part is the regressor, and the second part is the nonlinear function. The regressor, the object of the regressor is to take the input and the output data lagging in time, because we want something capture the dynamics in the data. And the nonlinear function, the objective of the nonlinear function to capture the highly nonlinearities like saturation and diffuse or anything else in the data, and also coupling. Like we know in the quadcopter, there are a few coupling between the 6 axes, rotations and translations. This is the we know that in the linear autoregressive models, the relationship between the prediction and the output is linear function. But here, we have a nonlinear functions of the time lags of the input and the output. What we found in the literatures, they used a non-linear RX models, which can be done as follows. The first way, they used discrete state space model with neural network. At the level of the input of the neural network, they used discrete state space to make the system able to capture the dynamics in data. Other methods used autoregressive models with neural network. The same thing. The third method is using radial basis functions neural network. The gap that we found that there is no one uses long short-term memory structure to identify the 6 degree of freedom quadcopter, nor using highly informative exciting signals. This is some of the literatures we have. So our goal is to design a long short-term memory-based system identification model for quadcopter dynamics. Then designing excitation, design excitation and a data collection procedure. We need something help us to get rich information from the quadcopter's dynamics. Then evaluate and then training, validation, and testing the pre-trained model. Our benchmark paper is a paper published in 2020 by Muhammad Berian, which titled by Neural Network-Based System Identification for Quadcopter. This method summarized by this figure. They provide an input signal to the system, then collecting data, then selecting the model structure. The model structure has two components, as we said previously: the regressors at the level of the neural network and the and the neural network. The regressors capture the dynamics and the temporal dependencies between data, and the neural networks work as a nonlinear function. Then when they do prediction, compare the prediction with the actual, taking the error and using backpropagation algorithm to adjust the weights of the neural network. How can we start our method to collect the data? At the beginning, we design the experiment, as you can see here. At the beginning, we stabilize the drone using the ID controller with the optimized gains using PSO, particle square optimization, to get the best set of BID parameters to make the system work well. Then operate the system under pseudo-random binary signal like signals, which is a persistent exciting signal. Also, we take into consideration the physical constraints to operate the system within the safe region. We don't want something exciting the system and make it diverge, unstable. By the way, the method has been done as follows. We give for the horizontal controller x desired y desired 0, 0, and the persistent exciting signal given only for the altitude controller and the attitude controller as a perturbation. This is the command coming from the controller, but we add summation here to adjust this control signal using the persistent exciting signal. Here, the overall methodology for doing system identification for Quadcopter. We provide a data input persistent exciting signals to the real system, but in our case, not real system, it is a model. As a physical model, then collecting the actual output, which is rich. There is a table here, rich in terms of information. Then we select the model structure. Our model structure is long, short-term memory. When we do a prediction, step ahead prediction, we need all the previous Y output and the previous input. Not only t minus 1, t minus 1, t minus 2, t minus 3, depend on the width of the system of on the window of the identification. To do one step ahead prediction, then we compare the actual with the predicted, and we have this cost function or least square. This is the identification method. Here is the model structure M. This is the real system S. This is the experimental design X. Then we used backpropagation through time because in LSTM we cannot use the backpropagation and normal form because here we have a time dependencies and sequential learning to adjust the parameter of this non-linear function until we minimize the error to 0. Collecting the data pre-processing. At the beginning, we collecting the data, then we do data pre-processing by filtering and normalization, then selecting the model structure, then parameter estimation, model validation, and model test and evaluation. How we can start exciting the system? We use a combination of sine wave and cosine wave signals with different frequencies. Then we set up the simulation in MATLAB where the time sampling was 0.01 second and the simulation time was for 1000 seconds. We collect the data. The data that we have collected is the control commands, the thrust and the moments. By the way, not the motor speed, because we extract the motor mixing algorithm. Just the moment, the torques and the thrust. Then the output is the 12-state vector: position, velocities, Euler angles, and angular rates. Here, the structure of the persistent excitation signals. As you can see here, we excite the attitude control and the altitude controller and the attitude controller. This is the main signal that we use to do excitation of the system. It is a combination of sine wave and cosine wave with random frequency and amplitude, but with small variation to avoid the system to be diverge and fall down. Here the simulation for doing excitation to the system. Now we come to LSTM, long short-term memory structure. This unit has the capabilities for do one-step ahead prediction. By providing it the previous output and the current input, we do one-step ahead prediction to the output. It is a non-linear function like the regressor and with the neural network. It has the same working principles. The upward bar, or it's called the cell state. The cell state works as finite impulse response, which is infinite impulse response, which is the long-term memory. It depends on the previous output. It depends on the previous output and some activation and information coming from the current input. As we know, infinite impulse response, and we can take an example for example, this system 0.6 y of t minus 1 plus impulse of t. If we give an impulse of t at impulse of t equal at time equal 0, an impulse function with the magnitude is equal to 1, and then we calculate the iteration every time for t equal 1, t equal 2, t equal 3. We can see that the system is decay with time, geometrically decay, but we never will reach to 0 because this is short long-term memory. But if we use y of t equal to a combination of lag input and giving this system impulse response, the system only still have a response for 3 iterations and it will vanish after that. This is the long-term memory, and the downward bar is the short-term memory, which is finite impulse response, which is a combination of lagged inputs, and the infinite impulse response is combinations of lagged outputs. This is we have here 4 gates: the forget gate, the input gate, and the state candidate gate, and the output gate. The forget gate helps us to forget the old information. The input gate helps us to give scaling for the new information and useful information that we want to insert into the long-term memory. And the output gate do the one-step ahead prediction. Here is the equation of this flow. Loss and gain. This is the loss function for the project. It's basically calculate the errors between the actual and the predicted one. And here is how the LSTM do one-step ahead prediction, simply by import the data with. This is an example. This is an example just to show you how we import the data to the networks. So by simply import 30 days to the first unit, and then get day 31. After that, we use the previous data from the first unit and using the current data from our side to predict the day 32, and same with the third unit. And the LSTM setup that we used is we split the data first for 70% training, 15 validation, and 15 testing. The networks, this is an example just to show you the network layers. So we have 2 LSTM layers with 128 units for each, and then in between we have a drop rate layers with 0.2 and 0.3. After that, we have two fully connected layers that convert from 128 neurons to 64, and then convert from 64 to 12 outputs, which is our states. The hyperparameters are, as you can see, and this is the result. The training process, as you can see, this is the root mean square or persistent iteration. It starts high, but converge and stay at 0.0182, and same with the loss persistent iteration. This is the root mean square for each state. The maximum one is the y-axis. It got 3.3, and the minimum one is the theta, which is 0.2. And here is the figures that show us the errors between the predicted and the actual outputs for our networks. And this is the first state with its derivative, and y-axis with its derivative, the phi, and the other states, theta and psi. And this is a short figure that shows us the closed loop of the model or the trained model, and it's trying to minimize the error and to follow the trajectory. Feature works using the geometric approach for system identification on the manifold SCE3 in order to apply highly aggressive excitation, sign signals, and avoiding singularities. This is the reference, and that's it, and thank you.
Can you explain to me the path A?
The drop outlier, it is like the forgetting factor or dropping of some of the neurons. So it's 0.2 here for the first layer. So it basically turn off the 20% of the neurons of the layer. We used it for regularization or do generalization when the system goes through overfitting. We cancel out some neurons with its weights from the previous layer. We have here 128 units. So if the drop rate is 0.2, 20% of this layer will be cancelled out to make the system avoid overfitting.
So you are by default assuming that the system is overfitting.
Yes. No, but this is done automatically. This is using the validation data. During the training, the validation data tells us or tell the backpropagation algorithm there are some overfitting in the network. So we have to cancel out some units from the.
So this is my question. How the system detects there is
overfit. We split the data for training and validation and testing. The training data used to adjust the weight using backpropagation algorithm. And at the end of each epoch, we insert the validation data, which the network didn't see it before, and try to do prediction like this.
overfitting detection occurs when the difference accuracy between the training and validation exceeds a certain threshold defined in the
I will give a simple example. If we have a neural network, this box, and we provide the input and output data. We have here the target, and we calculate the error feed them back to the back propagation algorithm to adjust the weights in this network. So if my data, if I have a lot of neurons in this network during the training, maybe some paths in the network will not train. The back propagation only adjusts the weights of some paths in the network, and some paths still without training. So maybe when I give this neural network an input that the network haven't trained on it, it will give me a bad prediction because we didn't generalize, make this network generalize, do generalization on the data. So drop out the method is cancel out some neurons at the validation state.
So this work you have done it only for this work?
Yes.
Is it part of your research?
No. I am thinking about using the geometric approach because the problem here is when you use the Euler angles, there are singularities happens at 90 or minus 90 degree. So if we want the drone to flip out, down, and do higher maneuverabilities, we have to use the geometric approach on SE3 on the manifold.
You don't have to use it. You don't.
Huh?
You don't have. You can still do it without geometry.
Yes, yes. So we can.
You can use change preview the pattern.
Yes, quaternion. Quaternion it works well.
Why you didn't use air stop to avoid overfitting?
We can use it. I think we use it in the during the training process. If there is no progress during the training, we make the algorithm stop automatically.
Yeah, you already simulated all of this method, or you just saying you will use it. So you have graphs for.
Yes, we have graphs of the training. This is the training progress. But we didn't add. Yes, we didn't add the air stop.
Yeah, yeah.
Because there here is for a long time we have the same label of the RMSE.
Very good work.
ما شاء الله.
أتفضل.